Welcome to physics class again. In today's class, we will try to discuss about the moving coil galvanometer and conversion of it into ammeter and voltmeter. And this is in the chapter number 4, moving charges and magnetism for class 12. And rather it is the last part of this chapter. So let's start with the moving coil galvanometer first. Moving coil galvanometer is also called deadbeat galvanometer, and it is an instrument used to detect and measure very small current, electric current. So your moving coil galvanometer is an electrical instrument used for detection and measurement of small electric current. What is the principle of this moving coil galvanometer? The principle of moving coil galvanometer is that current carrying coil, when placed inside a uniform magnetic field, it experiences a torque. We have learned about torque, right? A torque experienced by a rectangular coil, current carrying rectangular coil placed inside a uniform experience a torque, right? So that principle is used in the making of this moving coil galvanometer. So your principle of moving coil galvanometer is that current carrying coil placed inside a uniform magnetic field experience a torque. Now let's see about the construction of the moving coil galvanometer. Now in this moving coil galvanometer, it consists of a coil PQRS prime having a large number of turns of insulated copper wire wound over a non-magnetic rectangular or circular frame, or it may be preferably brass, over a laminated soft iron core, capital L, and suspended from a torsion head, capital H. This is a torsion head, capital H, by means of a suspension fiber of phosphor bronze. This connecting wire, it is made up of phosphor bronze fiber. And why we use phosphor bronze fiber instead of taking simply copper wire or aluminum wire or silver wire, it has a specific reason, and while we go through the topic, I will tell you why this phosphor bronze is used. Actually, this phosphor bronze is used because so as to have that minimum torsional couple per unit angular twist. Okay, this will come when we go through the topic in depth. Okay, we will find it. So what happened, this is suspended from a torsional head, capital H, okay, by using of what, this phosphor bronze strips, such that the coil is placed inside a strong magnetic field NS, and this magnetic field, it is in the shape of cylinder. So cylindrical pole pieces, cylindrical strong pole pieces will be used to place this rectangular coil in between it, and these cylindrical pole pieces is used so as to have that radial magnetic field. And when we go to this again, I will tell you why it is radial. Okay, the lower end of this rectangular coil S, okay, rectangular coil PQRS prime, is connected to a hairspring S prime, okay, and it is connected to it to one of the terminal T2, and it is internally connected here. You will see that this red color wire, okay, this is internally connected with that of the terminal T2, and the other end of the coil is connected to this phosphor bronze fiber through this torsional head, and it is again internally connected to the terminal T1. So your T1 and T2 are the connecting terminal of whose current to be measured, okay, is to be connected in these two terminals. And now a concave mirror, okay, capital M, here it is denoted here, a capital M is attached on to the phosphor bronze suspension fiber to note the deflection of the coil, right? using a lamb and scale arrangement. And I will tell you after this slide what is lamb and scale arrangement. Okay, after this I will tell you everything. Okay, but let's try to have that description first. Lamb and arrangement, and the whole arrangement of this moving coil galvanometer is enclosed in a non-metallic, okay, non-metallic case provided with a leveling screw. So as I told you about that radial magnetic field, if you look from the top view, this is a cross section of that top view, you will see these as a cylindrical pole pieces, north pole, and this side as the south pole of the cylindrical pole pieces. So if you look from the top, that means top view, then what happened, you will see this as the rectangular coil, this rectangular shape, black in color. This is nothing but this is your rectangular coil. Okay, this one is a rectangular coil, and this you will see this in the form of a circular like this. Okay, so what happened, all the magnetic line of force coming out or emitted out from the north pole to the south pole, it will be along its radius, so we call it that as radial magnetic field. Why it is taken as radial magnetic field? Because the torque experienced by the rectangular coil, okay, when placed inside the uniform magnetic field, then what happened, a torque will be experienced, and that torque will be maximum when that current carrying rectangular coil, okay, its plane is kept in parallel to the magnetic line of force. This red line doesn't show you that magnetic line of force. Magnetic line of force never crosses each other, but I am drawing here this just to make you see that this magnetic field which comes out here, another magnetic field which goes like this, these two seems to be in the same line, see. Okay, and if it is here, it will be like this, no doubt. For this one, it is also along this, but the magnetic line of force, it goes and it comes in like this, and it goes in this way. Got it? So what happened, this red line will show you the plane of the rectangular coil at different orientation. When the coil is like this, the magnetic line of force will be along this. When the coil is somewhere here in this, okay, when the rectangular coil, then what happened, that rectangular coil, its plane will be also in the magnetic field of this one. Got it? So that's why when we take it like this in the radial magnetic field, because to have that maximum torque experienced by that rectangular current carrying coil when placed inside the magnetic field, that is why we take it as a radial magnetic field. Now this is the actual diagram of that moving coil galvanometer. Okay, so the whole arrangement is enclosed inside a non-metallic case provided with the leveling screws. You will see somewhere here like this. Okay, so that when we level it, what happened, the rectangular coil inside the magnetic field will rotate smoothly or freely. Got it? Yes. Next we will go to that part of the theory. Now yes, now let I be the current flowing through the coil, B be the magnetic field induction, and L and B the length and the breadth respectively of the rectangular coil, capital N be the total number of turns, so that what happened, A will be equal to length into breadth, area of the coil. Okay, as your rectangular coil will be having its area length into its breadth, so this will be equal to capital A, which is equal to what, area of the rectangular coil. As the plane of the rectangular coil is parallel to the magnetic field, the side PS prime and QR will not experience any force, but the sides PQ and RS prime will experience maximum force perpendicular to the coil. Why? Because the plane of the coil, okay, is parallel to the direction of the magnetic field induction, so the side PQ and RS will experience maximum force perpendicular to the coil. Got it? So we have already learned about this in the previous video, that the rectangular coil, okay, when placed inside the uniform magnetic field, it experiences a torque, and the force will be perpendicular to the plane of the coil, right? So the force on F, the force on PQ, it should be, let's make it that force as F, okay, on PQ and RS, they are equal in magnitude, and that F will be equal to NBIL, okay. We might have remember that formula as IL cross B, but this, as there is not a single turn, there are large number of turns. Let's take it that capital N is the total number of turns, okay, as I have mentioned here. So the total force will be what? NBIL sine of 90 degree. Sine 90 degree is 1, so we remove it, okay. So NBIL, okay, but opposite in direction and acted at two different points constitute a couple. So one force will be acting onto the side PQ, and that same force, okay, but opposite in direction, okay, will be acted on the side RS prime. So these two equal and opposite forces acted at two different points of the same body will constitute a couple, and this couple will try to deflect the coil, and it is known as what? The deflecting couple. Now, as the couple is acted onto the coil, we can find out the deflecting torque. Deflecting torque, by formula we know it that torque will be equal to moment of that deflecting couple, and that moment of a deflecting couple will be equal to either of the magnitude of the force into perpendicular distance, right? So either of the magnitude of the force is this one, okay, and BIL times the perpendicular distance now is your breadth of the rectangular coil. So what happened when you multiply it with the length and breadth? We have said that length into breadth is nothing but it is the area of the rectangular coil. So your deflecting torque will be equal to NBIA. Got it? Now when the coil deflects, the suspension fiber, okay, gets twisted. The suspension fiber gets twisted, and what happened? On account of elasticity, due to that of elasticity, a restoring couple is set up in the fiber, okay. If alpha is the angle of twist, then the restoring torque will be equal to, again, moment of the restoring couple, which is equal to K alpha, where K is nothing but this is a restoring couple per unit angular twist, known as torsional constant. This K is known as torsional constant, and this is defined as what? The restoring couple per unit angular twist. In the previous slide, I told you that we use phosphor bronze fiber. Why we use phosphor bronze fiber instead of copper or silver? Because this phosphor bronze fiber has small value of this torsional constant, small k. In fact, if we use quartz again, it will be much smaller, okay. So either you can use phosphor bronze fiber or quartz fiber for the suspension of that rectangular coil in the moving coil galvanometer. Why? Because just to have that what? Smaller or less torsional constant. Torsional constant means what? Restoring couple per unit angular twist, okay. So as to have what? Higher sensitivity. We will come all this again when we come to that sensitivity, okay. So let's try to find it out. Next, what happened in equilibrium, or for the state of equilibrium of the coil? What happened? This deflecting torque, okay, will be equal to the restoring torque. Deflecting torque will be equal to restoring torque. In that situation, it will be in equilibrium, and there will not be any what? Change in the direction of the coil. The coil will be stationary there. That means at equilibrium, this deflecting torque will be balanced by this restoring force. That means they are equal. So what happened for equilibrium? The deflecting torque must be equal to what? Restoring torque. So from that, NBIA will be equal to K alpha. Got it? Or we can express I is equal to small k alpha times NBA, where what is this small k? Small k is nothing but this is a torsional constant, or you can call it this as restoring couple per unit angular twist, right? And this k divided by NBA, okay, k divided by NBA, this k is also constant. Total number of turns of the moving coil galvanometer or rectangular coil, that is also constant. Magnetic field induction produced by that cylindrical pole pieces, that will be also constant, as long as you are not changing that rectangular cylindrical pole pieces. This P will be also constant, A will be also constant. So this K divided by NBA, we can replace it by another constant, capital K, and this capital K is known as galvanometer constant. So for that particular galvanometer or moving coil galvanometer, this K will be constant, and we call it that K as what? Moving coil galvanometer constant, or simply you can call it as galvanometer constant. So then from this last expression, we found that your I is directly proportional to what? Alpha. Because what? I is equal to K alpha. Capital K is a constant, so we can express as what? I directly proportional to alpha. Or you can say alpha. Alpha means what? Deflection. So your deflection in the moving coil galvanometer is directly proportional to the amount of the current that is flowing through the rectangular coil. So what happened? Thus the deflection of the moving coil galvanometer is proportional to the current flowing through it. Got it? Yes. As deflection is directly proportional to the current through the coil, so we can use what? The linear scale in galvanometer. So if you are asked why linear scale is used in the galvanometer, then you can say that your deflection in the galvanometer of the rectangular coil is directly proportional to the current flowing through the coil. Clear? So the scale is calibrated, okay, to give the values of current, right? Direct values of the current, you can see. Now this measurement of scale in the case of your moving coil galvanometer, I told you that in the construction that it can be used by means of what? Lamb and scale arrangement. So what is this lamb and scale arrangement? It is an arrangement of what? Lamb along with a scale here like this. So what happened? This is the lamb, okay, this is the lamb. It may be either of that of a laser or by a simple normal lamb, okay. So this is a lamb here, and it is fixed on a vertical stand like this, and above it you can have a transparent scale that you are having, just like your mathematical scale like that, but this one is a little bit longer one. So this is a transparent, and it is graduated there, the scale, okay, marks are graduated there. So what happened when this lamp is lighted? Then your moving coil galvanometer is toward you, and that concave mirror, okay, the reflecting side is facing toward this lamp. So when the lamp is illuminated, and if it is pointed onto that concave mirror, then the reflected light should incident on to this scale. So when the current is passed through the moving coil galvanometer, the spot of the reflected light from the concave mirror will be incident onto it, and you can easily see the number of this deflection or number of that division onto this scale that will give you the deflection of this rectangular coil, okay, rather by deflection of this what moving coil galvanometer can be measured from it. So that is nothing but that is a lamb and scale arrangement for measuring the what deflection of the current in the moving coil galvanometer. Now let's go to that of current sensitivity. What is this current sensitivity? The current sensitivity of a moving coil galvanometer is the deflection of the meter per unit current. When we say sensitivity, sensitivity is nothing for a small given input. If there is a large deflection, then we say that that is what? More sensitive. So in the current sensitivity of a galvanometer, what happened? That will be more sensitive if it gives what? Large deflection for a small current, okay. The input, if the input to the moving coil galvanometer is a small current, and if it gives a large deflection, then we said that that sensitivity is very high. Okay, for current sensitivity, okay, the current sensitivity of a meter or a moving coil galvanometer is the deflection of the meter per unit current. That is what happened, alpha by I, that means deflection per unit current will be equal to NBIA by K. This is from that expression, NBIA is equal to K alpha. Deflecting torque is equal to restoring torque. Okay, NBIA, okay, equal to K alpha. Just we have done that one now. So from that, alpha by I, that means deflection per unit current, will be equal to NBA by K, right? So if you find out this, what alpha by I, then that will be the formula for current sensitivity, and it can be expressed as NBA by K. So what happened, this current sensitivity is directly proportional to the total number of turns of that moving coil galvanometer, the strength of the magnetic field B, the area of the rectangular coil, and inversely proportional to the torsional constant, or rather your restoring torque per unit angular twist. So smaller this K, higher will be the current sensitivity, right? Smaller the value of K, as this is inversely proportional to the current sensitivity. So what happens, smaller this value, torsional constant, higher will be the current sensitivity. That is why we take it that as a phosphor bronze fiber for that suspension of the rectangular coil, right? Or you can even take that coarse so as to have again smaller value of this K, right? But this NBA, even though this NBA are directly proportional to the current sensitivity, there is a maximum limit. You cannot increase this total number of turns as your wish. Why? Because if you met that total number of turns more and more, that means it will give you the longer length of the rectangular coil, which will increase the length of the rectangular coil rather. So what happened, it will give you larger resistance again. If it is of large resistance, then small current may not be able to flow through that rectangular coil, and it may not respond to that deflection again for a small current, right? So like that, you cannot increase this NA as your wish. There is a maximum limit. No doubt for the magnetic field induction, you can use a stronger pole pieces, okay, so as to have that larger value of B. So we will come again this again later on, okay? But for the time being, let's go to the voltage sensitivity. Sensitivity are of two types. The first one is that one we have just discussed, current sensitivity, and the second one is what, voltage sensitivity. And similar to this voltage sensitivity, current sensitivity, your voltage sensitivity may be also defined as a deflection of the meter per unit voltage. In the case of current sensitivity, it is a deflection of the meter per unit current. Here in the voltage sensitivity, it will be deflection of the meter per unit voltage. Okay, so it is nothing but this will be alpha divided by V will be equal to what, alpha divided by IR. From here you can take it, okay? So alpha divided by V from Ohm's law, it will be equal to IR, no? So I is the current flowing and R is what? This is the resistance of the rectangular coil, R. So what happened? Alpha by V will be equal to alpha by IR. So from this current sensitivity, you just divide it by R and you will get it what? Your voltage sensitivity. Same is the case here also. Voltage sensitivity is directly proportional to N, B and A, and inversely proportional to what? That torsional constant, inversely proportional to the resistance of the rectangular coil, moving coil, okay? So what happened? If one try to increases this number of turns so as to have that current sensitivity or voltage sensitivity, R will be again increase. If R again increase, as this is directly proportional, what happened? Your voltage sensitivity will again decrease. So what happened? Therefore, from the above two equations, from these two equations, as I said, that sensitivity can be increased by increasing what? NBA, because as they are directly proportional to the sensitivity, either it may be current or voltage sensitivity, and decreasing K and R, okay, as they are inversely proportional. What happens if you decrease these K and R? Then alpha, okay, by I, or alpha by your V will be increased. But N and A cannot be increased much, as this will increase the length of the coil, and so resistance will be also increased, which will not correspond or respond, to the weak currents. Okay, if R is large, then what happens, that small current may not be able to pass through that rectangular coil due to that high resistance, and so it will not respond to the weak current to be measured. Okay, B, magnetic field induction, can be increased by using a strong magnetic pole pieces, and K can be decreased by using phosphor bronze strip or quartz suspension fiber, as I told you. Okay, now let's see, in the case of this moving coil galvanometer that we are using in our lab, that are all what we call as Western type of moving coil galvanometer. It may be also called as pointer galvanometer or pivoted moving coil galvanometer. In this type of galvanometer, what happened, the coil is pivoted between the two ball bearings. Okay, two ball bearings, a light aluminum pointer is attached to the moving coil. The controlling couple is provided with the help of springs, such like this blue in colors. You might have seen this blue in colors. Okay, here the two blue colors. So these two will help you to pivot this moving this rectangular coil in that moving coil galvanometer. Got it? And this one of the end of the rectangular coil here, it will be connected to this spring, and it will be connected to the terminals. Either you can take it as terminal T1, and the other end of the rectangular coil is again connected to this coil, which is connected to the terminal. You can take it this as T2. Got it? Like this, we use it as moving coil galvanometer in the case of what? A laboratory that we are using. These are not so much sensitive, okay, as that of moving coil galvanometer that we have shown in the previous one. Okay, that one, by using your lamp and scale arrangement, the sensitivity can be made very large. Large deflection can be obtained by increasing the distance between that moving coil galvanometer and that lamp and scale arrangement. Okay, that lamp and scale, if you increase the distance, then what happens, the deflected or the reflected light may increase its deflection. Okay, the degree of deflection, or rather the angle of deflection can be increased. Got it? Yes, that is the sensitivity of the moving coil galvanometer. So your moving coil galvanometer is very sensitive for a small current. Also, if you increase the distance between the rectangular moving the distance between the concave mirror and the lamp and scale arrangement, then what happens, deflection will be very large. Now let's see about the conversion of galvanometer into ammeter and voltmeter. The first one is into ammeter. So what happens when this galvanometer, this G denotes the galvanometer, and the resistance of the galvanometer itself also is denoted by this capital G. Okay, so what happens when this galvanometer is connected with a small or a low value resistance? Okay, then the whole arrangement can be used to measure current, and that whole arrangement we call it as what? Ammeter. So this is the circuit diagram for a conversion of galvanometer into ammeter, and this low resistance that is connected parallel to the galvanometer, we call it that as shunt resistance. So your shunted galvanometer is nothing but it is equivalent to an ammeter. Now let's take it that this capital I is the maximum current to be measured by a galvanometer. Now in order to convert this galvanometer into an ammeter, that much amount of the capital I, okay, that is the maximum current to be measured by that converted galvanometer, or rather by your ammeter. Okay, and as this is a maximum value, what happened, the range of that ammeter will be from 0 to capital I. Got it? Yes. To do so, that means to convert this galvanometer into ammeter, a low resistance called shunt resistance is connected in parallel with the galvanometer, so that Ig should pass through the galvanometer G. your Ig is nothing but this is the full scale deflection. Full scale deflection means when current Ig is passed through this galvanometer, then your galvanometer should read to the maximum value. Okay, so this Ig is the galvanometer, okay, current, that means the current that is passing through this galvanometer G, and the remaining current, okay, will pass through the shunt from your Kirchhoff's current law, the first law. Okay, the current that is I is coming here, some part Ig is going through this galvanometer, the other remaining part should go to the other branch, right? So that what happen, I will be equal to Ig plus I minus Ig, right? So what happened, the remaining current I minus Ig will pass through the shunt resistance, right? So then what happened, as these two, the galvanometer and the shunt, are connected in parallel, what happened, the potential difference across these two point A and B must be having the same value. That means Ig is the current passing through this galvanometer, so Ig times G will be equal to what, S times of I minus Ig. That means potential difference across shunt must be equal to potential difference across G, right? So by your Ohm's law, potential difference is equal to current into resistance. So Ig into capital G will be equal to I minus Ig times of S. So from this expression you can easily find out S, the shunt resistance. The value of shunt resistance will be equal to what, Ig capital G divided by I minus Ig, right? Like this you can find out the expression of the shunt resistance. Got it? The galvanometer, which was recording maximum current Ig before conversion, okay, before conversion, what happened, I told you that Ig is a full scale deflection, right? That means this is the amount of current that will give you the full scale deflection of this galvanometer before conversion. Okay, so what happened, into ammeter will record the maximum current when it converts into what, your ammeter with this shunt resistance connected in parallel, then the maximum full scale deflection will be what, this current I. So your 0 to I will be the range of that converted galvanometer into ammeter, right? And if you want to find out the effective resistance of this ammeter, then what happened, as this capital G, which is also known as the resistance of the galvanometer, and that of this shunt resistance, as they are connected in parallel, then you need to find out the equivalent resistance of these two connected resistance in parallel. How will you do that? You can do like this. See, your, let's take it that Rp is what, the effective resistance of this ammeter. So as these two R and G are connected in parallel, so 1 by R P will be equal to what, 1 by S plus 1 by G, right? 1 by G. So what happened, your 1 by RP will be equal to what, SG divided by S plus G, right? So if you want to find out RP, then reciprocal of this, that means SG divided by what, G plus S. That will be the expression coming up. So your RP will be equal to what, GS divided by G plus S. Now we know that this S is a very small resistance. What happened when this S is very small resistance or low resistance, what happened, the sum of these two will be approximately equal to G. Got it? And if that G and this G in the numerator, if these two are cancelled, then it will be approximately equal to the small resistance, shunt resistance S. So what happened, your resistance of this, rather effective resistance of an ammeter is small, okay, approximately equal to that of the shunted resistance. In an ideal ammeter, what happened, the resistance of an ideal ammeter will be equal to what, 0. Got it? Yes. Let's see for a conversion of this galvanometer into an ammeter. When a high resistance capital R is connected in series with a galvanometer, then the resulting okay, arrangement, we call it that as voltmeter. What is this Ig? It is similar with that previous one. Ig is nothing but this is the full scale deflection, okay, of the current when passes through the galvanometer alone. So Ig is known as full scale deflection. So what happens when this large resistance R is connected to this galvanometer, then your Ig will not give you a full scale deflection. Rather, we will try to find out what the potential difference across these combination of G and R. Okay, so what happens if capital V is the full scale, okay, deflection for that galvanometer, then what happen, that converted galvanometer into ammeter will have the range of what, V, 0 to V I should say. Okay, so let's see in the next. What happen, let capital G, okay, be the resistance of the galvanometer, V be the potential difference to be measured, okay, or rather you can take it this as the range of that particular voltmeter, and Ig is the current for full scale deflection, where R is the high resistance that is connected in series with the galvanometer. So by applying your Ohm's law, your Ig will be equal to what, V by Ig, G plus R. That Ohm's law, V will be equal to IR, no? That R is nothing but this is the combination of G plus R, because as this R connected in series, right? So from there you can find out this high resistance R, V by Ig minus what, R. This is very easy. You can easily find out. So V by Ig from this expression, okay, V by Ig will be equal to what, G plus capital R. So if you want to find out R, then this will be equal to what, V by Ig minus of what, G. So that is what it is done here. Got it? So you can easily do, or you can easily find out the expression for finding what, for finding this high resistance that to be connected in series to the galvanometer, so as to make it that as galvanometer as what, voltmeter. So that is what it is given here. Okay, and suppose what happen if you want to find out this effective resistance of this voltmeter, then as these two are connected in series, as I told you, that your RV, equivalent resistance, okay, or effective resistance of that voltmeter, V for voltmeter, will be equal to what, G plus R. Your G is also a high resistance, your capital R is also high resistance. So what happened, the effective resistance of this voltmeter is very high. Got it? In an ideal voltmeter, it will be having what, infinite resistance. Okay, as voltmeter is having very large resistance, we usually connect this voltmeter with the circuit parallel. Okay, parallel with the circuit, whereas your ammeter is having a low resistance device. Okay, then what happen, your ammeter will be connected in series with the circuit. Okay, if one asks you why voltmeter is connected in parallel, why ammeter is connected in series with the circuit, then you have to say all these things. Okay, voltmeter is always connected in parallel to the circuit because voltmeter is a very high resistance electrical measuring device, so we need to connect it in parallel. Okay, and why ammeter is connected in series, because ammeter is a very low resistance device, and so we have to connect it in series with the circuit. So connecting a low resistance device in circuit will not give you any harm in those parameters of current, potential difference, whatnots. Okay, so with this we will come to the end of our today's topic, and let's wind it up here. Okay, thank you.